Okay, let's do some work with integrals and volumes. So let's write that up here. So we're going to work on integrals and volume. Okay, so what we should know already is that volume, so let's see, we should already know that the volume of an object is the amount of three-dimensional spaces, the amount of unit cubes that can fit in it, and basically for any cylinder or prism, so for cylinders and prisms, which have a constant cross section, they're the same bottom to top, the volume it will be equal to the base area times the height. Okay, and that's just because the base area tells me how many unit squares fit in the base. The height will tell me how many unit cubes I can stack tall. So this is something we should already know. Okay, but for integrals and volume, what if it's not a cylinder or prism? And for our purposes, let's take a look at the cone. So we know the area or the volume of a cone is 1/3 pi r squared times h. We all should know that. So let's take a look at the cone. Example, cone. And let's look at the cone that has radius 1 and height 2. And for our purposes, let's actually look at that cone on its side. You can look at it up and down, but let's look at it over on its side. So we know that the cone should look something like this. And I can actually do a little bit of shading to make it even closer to what a cone actually should look like. Okay, so that's what a cone pretty much looks like. Now, why is this volume equal to 1/3 base area times height? Or why is it equal to 1/3 pi r squared h? Well, let's take a look at a cone, and we'll figure out a way to actually come up with this. We're going to just do it for our specific numbers because we don't care about a cone as much as we care about any object, but let's look at a cone. Alright, same cone, you can see the radius here is 1, and the height, it's a little bit hard to see, but out here will be 2. And here's the idea. If you remember when we talked about areas, or we haven't talked about them in these videos yet, but we were able to break up any two-dimensional shape into rectangles. And for this, I'll be able to break up any three-dimensional solid into, in this case I'll use cylinders, I might have to use prisms, or something that has a constant cross-section. But for this case, let's look at this. So a cone, if I were to use 2 cylinders, we can see that I can start approximating the volume of the cone because I know the cylinder volume and I can calculate the volume of this left cylinder, this right cylinder, and use it as an estimate. But you see that we are actually way overestimating the volume of this cone. We have all this extra space around the cone. And just like with integrals in area, we can fix that quite easily by upping the number of cylinders. So let's go up from 2 to 4, and we'll see that let's see if we can click on this. we'll see that the cylinders are now a much better approximation for the cone. They look more cone-shaped. We still have a little bit of over measurement here, but we're closer. And if I were to go, let's go up to 8 instead of 4. So instead of 4, let's do 8. And we can see that it's an even better approximation for the volume of this cone. Okay, we still have some extra space, but it's even closer. And go up to 16, go up to 32. So we can see that as we get out to an infinite number of cylinders, we'll eventually get to the volume here. And the way we can do this more analytically, more algebraically now is, so we know that for one of these cones, okay, let's look at a little graph and use that. So for this idea right here, if I were to look at this graph, need to go from 1 to -1 in y and go out to 2 in x. Okay. So if I were to look in at this, this is basically the cross section of the cone cut right down the middle. And what we can see here is that for any one of our cylinders, and our cylinders were going right around here, the volume of that cylinder is just going to be based on this radius and this height. So the volume for one cylinder, so I'll say volume 1, because we would have many, this looks like about 8 would fit in, will be still base 1 area times the height 1. In this case, is going to be pi r squared times height. But if we look at this in a little different light, for any one of my cylinders, this radius will actually equal this function. It equals the y value. Notice it is the distance from 0 up to this function. It will actually equal f of x. And the height here is actually going to be some sort of delta x. And so what this means is, and I'm going to write this, there is some area function. It's going to be, so area in terms of r is going to be pi r squared, but we will have an area in terms of x. Okay, I'll write it in here. So area in terms of x, well, this function, it's the line that goes through 1, or 0, 1, y-intercept of 1, with a slope of -1/2. So -1/2 x plus 1. And we already said that this function is equal to my radius at any x, so I can use that to qualify any of my the radii of my cylinders. So I can write this as pi times -1/2 x plus 1. But the big idea is this. The volume of any one of my cylinders is going to be some area function, in this case in terms of x, multiplied by the change in x. And we already talked about, as we get more and more cylinders, we get a better and better approximation. And so this approximation, so the volume will be approximately equal to the sum. And I'm not going to put limits on here because it's a little bit weird, but basically we're going to see what happens as we get more and more. Well, I'll put them in. So let's go from k equals 1 to n of my areas in terms of some x value multiplied by the change in x. But the more I pull in, the better my approximation becomes, and I can do that by taking the limit as this goes off to infinity, so getting bigger and bigger. But the more and more n's, the smaller and smaller my change in x comes until it becomes the infinitesimal dx. So this is still representing the height of each cylinder, it's just so small it's practically zero. And instead of having to take specific x values, I'm actually going to use the function a of x, and instead of taking the sum, as we go off to using an infinite number of intervals, we will go to the integral. So this right here is the major concept for this right here. The volume of any solid, so long as the solid is somewhat nice, we can't have huge jumps, holes, some stuff, will be the cross-sectional area, the integral of that from some starting to stopping point of the cross-sectional area, which will be the area of the base of our approximations, multiplied by dx, which will actually be the height of each of those. And if I went back to my example down here, I'm not going to evaluate this integral, but I would get that the volume is equal to the integral from 0 to 2. Notice, because I'm using x values, and that's the thing that's changing the radius, and so x goes from 0 to 2. And you can also think of that as the dx, so I'm talking about x starting and stopping values. The area function, ooh, I missed a squared here. The area function is right here, so I have pi times negative 1/2 x plus 1 squared dx. And if I evaluate, and I can't evaluate by hand, I'll show some examples afterwards where I do evaluate all of these. This would then give me the exact volume of a cone, which would, in this case, be 1/3 pi r squared h, because cones aren't that interesting. We know that already. But for some of our objects in here, it won't be something we already know. Okay, so the next, I guess, 8 videos will be examples of various ways to find volumes, and then we'll go into solids of revolution.